Okay, so today we're working on our efficiency problems. You should have already done the reading or looked over the notes, so you should be familiar with efficiency. So we're going to get right to it. Okay, when we do efficiency problems, our equation we're using is our efficiency equals our useful work output over our work input, and then we take it times 100 because we want it as a percent. So let's get right into this first example. Okay. We have a sailor uses a rope and a pulley to raise a sail that weighs 140 newtons. Okay. He finds that he must do 180 joules of work on the rope to raise the sail by 1 meter. What is the efficiency of the pulley? So let's start with what we know. Okay. Our first number is 140 newtons. Now, hopefully you remember that newtons are a unit of force. Okay. So we have force equals 140 newtons. Okay. My second number is 180 joules. Joules is our unit for work. So this is going to be work, but is it input or output? Okay. In the problem, it says that he must do 180 joules. So if it's what the sailor actually is doing or needs to apply, that would be our input. Okay. So our work input, or work in for short, is 180 joules. Okay. And then we're just left with our 1 meter. Meters is our unit for distance. So that's a distance. Okay. And we are trying to find the efficiency. So we don't know our efficiency yet. Okay. So if we look at our equation, you see that we need work output, work input. We have work input. We don't have work output. We have a force and a distance. So we need to do some calculations before we can plug things into our equation. Okay. Hopefully you remember our equation for work is work equals force times distance. Okay. We have force, we have distance. So our work output, or work out for short, is going to be 140 newtons times 1.0 meters, which will equal 140 joules. Okay, now we have everything that we need. We should be able to plug things into our equation. So we have efficiency equals our work output, which is 140 joules, over our work input, which is 180 joules, times 100. Okay. And I end up getting 77.77777, so I'm going to round. Okay. My joules cancel out, but we multiplied by 100 to make it a percent, so I better make it a percent. Don't forget sig figs. Okay, 140, 180, 1.0 all have 2 sig figs, so my answer better have 2 sig figs. So once I round, my efficiency should be 78%. Okay, next question. We have, if it takes 1,200 joules of work to lift a car high enough to change a tire, how much work must be done by the person operating the jack if the jack is 25% efficient? So again, let's start with what we know. So we have 1,200 joules, okay, and that's the amount of work to lift a car. So lifting the car, right, is our end goal. That's what we want to get to. So that's going to be our output. So my work out is going to be 1,200 joules. Okay, 25%, that's my efficiency. And we're trying to find how much work the person needs to do, right? How much work must be done by the person. So if it's how much is done by the person, that's what you're putting into it, that's your input work. So I should be able to plug everything in my equation right away this time. So I have 25 equals 1,200 joules over my input work times 100. Okay, so to solve this, first thing we want to do is get rid of that times 100, so we do the opposite, which is dividing. So I divide both sides by 100. That cancels out. I have 0.25 equals 1,200 joules over my input work. Okay, and then the easiest way to solve this is going to be probably to turn it into a proportion. Okay, so if I put 0.25 over 1, that's still 0.25, right? Anything divided by 1 is just that number. Okay, so now I have a proportion, so I can cross multiply my 1,200 by 1 and divide by that 0.25. So 1,200 times 1 is 1,200, divided by 0.25 should be 4,800. Okay, so that's going to be my input work. My unit for work, as always, is joules. Okay, double check your sig figs. 1,200 has 2 sig figs, 25% has 2 sig figs, 4,800 also has 2 sig figs, so we should be good to go. 4,800 joules. Okay, we have one last efficiency problem to do. So, a windmill has an efficiency of 37.5%. If a gust of wind does 125 joules of work on the blades of the windmill, how much output work can the windmill do as a result of the gust? So let's start with what we know. Okay, we have 37.5%, that is our efficiency. We have 125 joules of work. Now we don't have any people or no person in this example, but it says the gust of wind does the work, so that's still the work that is being done. Okay, so that's going to be our input. So we have our work in equals 125 joules. And then it asks for how much output work can the windmill do. So obviously we are looking for work out. Okay, so if you weren't positive if that was in or out for the 125, okay, if it's asking for output work, we only have 2 options, so obviously the 125 would have to be your input. So I can plug things in my equation right away again. I have 37.5 equals, this time I don't know my output work, over 125 joules times 100. So again, let's get rid of this 100 first by dividing both sides by 100. So I have 0.375 equals my output work over 125 joules. Okay, now I'm dividing over here, right? I want to get this work output by itself, so I'm dividing by 125 joules, so I have to do the opposite, which means I need to multiply both sides by 125 joules. Okay, that's going to cancel out to be 1. 125 times 0.375 ends up with 46.875. And that's joules because it's my output work. Okay. Sig figs. 37.5% has 3 sig figs. 125 joules has 3 sig figs, so my answer needs 3 sig figs. So we're going to end up with 46.9 joules for my output work. So there you have a few different examples for efficiency, solving for different variables. Hopefully this helps. I will also post the worked out problems like I did for kinetic energy and potential energy last week. So if you want to go back and see my work without having to sit through the whole video, you can do that. As always, let me know if you have any questions.